Hey everyone, welcome along to the June 2024 AMETEK Solid-State Controls webinar. Today we are going to discuss what's inside the box, and we're going to focus on our DPP systems today, our digital controlled PWM systems. Thank you, everybody, for joining us. As always, if you can put in the chat bar if you can hear me or not, that would be greatly appreciated. It seems pointless that I speak to myself. So if you can't hear me, I will be able to see that by people not posting in the chat bar. So while I await people arriving and saying that they can hear me or not, I'll do some introductions. So first of all, my name is Craig Williams. I am the Senior Technical Manager for AMETEK Solid-State Controls. Thank you very much, everybody, for saying you can hear me loud and clear. I'm based in the Stafford, Texas office, which is just outside of Houston on the southwest side. I have 22 years in the industrial UPS industry. I think 7 of those years, I'm into my 8th year with AMETEK Solid-State Controls. I've worked with all of the major UPS charger manufacturers over those 22 years, originally in the North Sea, off the coast of Scotland, went all over the North Sea, hopping from oil rig to oil rig. So that was fun. There will be a lag of around 30 seconds between you hearing my voice and me seeing a question. Basically, the platform we use is Webinar Jam, and they've got to process the signal, send it out to Android devices, Apple devices, and obviously Microsoft devices as well. So there is some processing time in getting that signal out, and it takes between 15 and 30 seconds. So when I speak, you will hear it probably 15 seconds later, and therefore I'll only see a question 15 seconds after it gets typed in. And for that reason, what I tend to do is always wait until the end to answer questions. And if I can ask you a favor, if you look on your chat bar, there is a chat tab and there is a Q&A tab. If you have a question, if you could please click on the Q&A tab and put the question in there, it separates the questions from the chat. So that would be appreciated. Okay. Webinar Jam, the platform that we use, does have a panic button. If for some reason I start to see something in the chat bar that says I can't hear you, or the signal is you can't see the presentation or something like that, then I can press the panic button, and what will happen is a new room will be created. Everyone will be invited to that room, and then we will carry on from where we left off. So that's how that works. Another very popular question is the webinar going to be recorded? And for all those who signed up for the webinar, you will be able to see the webinar recording pretty much straight away on the webinar platform. You'll get a link sent via email to say the webinar is available for you to rewatch. The problem with that video is they kind of treat it like a live webinar. You can press play, but you can't, from what I can recall, you can't fast forward, rewind, and go to specific parts of the presentation. So what our fantastic marketing team do, and London has posted it in the chat bar already, is they create a MP4, I think it is, I can't remember what file, and then basically they upload it to our YouTube channel, where you can see all of the previous webinars that we've done as well. And that way you can share it with people, you can pause, rewind, do whatever you want, just like a normal YouTube video. And another question that gets asked a lot, if these slides will be available as a PDF. This is proprietary information, so we don't give the PDFs out, but you can feel free to share. Okay. 1 second. And the last thing, the webinar should last around about 45 minutes to an hour, and it depends on how long I waffle on for, basically. I do appreciate your time, so I do try and keep it as concise as possible, and I do appreciate that you've taken time out of your day to come and watch this video. So sounds good. And just let everybody know, you can put your hand up and request to speak, but normally we just answer questions in the Q&A. We don't tend to let anybody speak on the webinar. Just wanted to answer that question. So today we're going to be looking inside the UPS systems. We're going to be identifying the following components: the input transformer, the charger and the associated PCBs, the printed circuit boards associated with the charger, the inverter and the printed circuit boards associated with the inverter bridge, then the inverter transformer, and then the static switch and the associated PCBs for the static switch. We won't go into great depth about how each of the charger, inverter, and static switch works. We do have separate videos for that I'll reference in the video as we go along. But hopefully this will give you a much better understanding of where things are on our UPS, what they do, and will give you more familiarity when you open the door. So you can see here, this is a single bay UPS. When we call it a single bay, that means it has one door, and if it had two doors, it would be called a double bay. And then we also have ones where very big, large systems may have two double bay cabinets bolted together. So this, I think this one is a 10 kVA DPP UPS, and it's just with the door open. So when you look in here, I'm just going to circle a few things so you can see on a general level where they are. So this here is the input transformer, okay? And right behind it, it's a little bit difficult to see here, but this transformer here is the inverter output transformer, okay? We have our rectifier bridge. Our charger is this bridge here, and the PCB associated with it is back there, okay? The inverter bridge is this section here, and the inverter control board and gate drive boards are here. It's difficult to see, and I'm going to blow all of these components up so you can see them in more detail. This is our static switch in the top right hand corner here, and then the brains of the system is this control board here. We call that on the newest systems, it's a color display board, but it's the interface to the outside world where the screen is connected to. Okay, so that's on a small 10 kVA system. On a larger, this is what we call a double bay, because this will have two doors attached to it. And I'll just go through the components on this one here too. So this transformer here is the input transformer. This is the inverter transformer, and this is an older system, so there are 3 chokes associated with the inverter transformer that help with the filtering of the inverter bridge. Okay, these are our AC capacitors that help with the filtering of the output also. Our charger rectifier bridge is this bridge here. Our inverter bridge is this bridge here, and here are the DC capacitors associated with the inverter bridge. And then we have our static switch on this one here. I know it's difficult to tell the difference between the rectifier, which is this one here, and the static switch, which is this one here. They're both on the same size heatsink, but we'll get into that in a little bit more depth in a moment. So hopefully that gives you a better understanding of when you open the door where the components are. Okay. So here is a single line diagram of our UPS systems. Obviously, we have our 480 volt three-phase input into the rectifier. The rectifier converts AC into DC, and the inverter converts DC back into AC. And then our static switch is how we choose between the inverter output or the bypass input to go to our load circuits. Once again, I'll explain these components in a bit more depth as we go through the presentation. So the first thing we're going to look at is the transformer, the input transformer. Okay. So there it is on the one line diagram to show you where it is in the grand scheme of things. And inside the 10 kVA single phase DPP system, this is where the terminations are. Okay, we have, I know it's very difficult to tell, but this here, it says TF1. So if you looked at the schematic diagram for your UPS, the component for the input transformer is labeled TF1, and we put that label on the transformer so you can identify it. Okay. Now our primary of the transformer is on this side here. Okay. So we have terminals 1, 2, and 3. Okay. So this is where our 480 volts from your MCC will be connected to the transformer. Okay. And you can actually see that it's connected on this bolt here, on this bolt here, and on this bolt here. Okay. That's how they're connected to the primary of the transformer. And then on the top side is the secondary, terminals 4, 5, and 6. Okay, and that is the secondary side of the transformer. And on that side, depending on what your DC bus is, if it's a standard 60 cell valve regulated or lead acid battery, then you're going to get around about 130 volts phase to phase on the secondary of the transformer. Okay. Now for the bigger three-phase system, TF1, you can see is labeled here. It has a choke mounted on top of it. Don't worry about that. That's just, it was a convenient place to have a choke mounted to it. Okay. I think, oh, no, I don't. So I think if I remember correctly, the primary, so the primary is on the right-hand side, and the secondary is on the left-hand side. And basically, a general rule of thumb is the larger the cable connected will give you a good idea of which is the primary and secondary, because as the voltage gets stepped down, then the current is going to go up on the secondary. So you're always going to see larger cables because it's going to carry more current on the secondary than the cables going to the primary. Okay. Now there are two main reasons to have an isolation transformer on the input to your UPS. Okay. And I've mentioned one of them before. So the majority of industrial stationary batteries are 60 cell, 120 volt DC nominal. So we have to be able to charge those batteries. Okay. And for power and efficiency, most industrial UPS manufacturers use 480 volts three-phase inputs to from the MCC to their charger. It just makes more sense. So therefore, the input transformer steps the voltage down to a value that allows us to charge the batteries with a little bit of wiggle room. We call it headroom. Okay. So basically, you can see here on the left-hand side, we've got the primary excuse my handwriting, and that's our 480 volts phase-to-phase input. And for a 60 cell lead acid battery, there we are there, then we are going to have roughly 130 volts phase to phase. Okay, now note that 130 volts RMS, which is what you measure with a Fluke 87 meter or anything else, actually has a peak, not a peak to peak, a peak voltage of 184 volts AC. So when we put that into a rectifier bridge, and I'm not going to get too much into the math of this because it can be brain numbing sometimes, but basically trust me when the equation is the output volts DC average is 1.35 times whatever the phase-to-phase voltage is here, which is 130 volts, times the cos of alpha. And the cos of alpha is basically the phase angle that the SCRs are fired at. So if you fire the SCRs as soon as so we have our sine wave there. If you fire your SCRs as soon as the sine wave starts to go up, then the cos of that will be, then the phase angle will be 0, and the cos of 0 is 1. So you will get 1.35 times 1.3 times 1. And I think that gives you about 175 volts DC on the output. Okay, so that's our upper limit. And then obviously, if we fired the gate later on in the cycle, that phase angle will go up. So the cos of the cosine of the phase angle will go down towards 0. So let's say at that point it's 0.3. So it would be 1.35 times 130 times 0.3, whatever that goes down to. That could be 80 volts DC. I don't know. I haven't done the calculation. I just want to show you that there is space. So wherever we fire the SCR on the sine wave, we can use an average calculation to find out what the voltage is. So that's why we use a step-down transformer. So we can get the voltage going into the rectifier bridge to be a voltage that we can work with our silicon controlled rectifiers or thyristors inside our rectifier bridge. Okay. And then I said that there's two reasons. The other major reason is transformers, isolation transformers in particular, also act as galvanic isolation. And that's the principle of isolating the functional sections of an electrical system to prevent direct current flow. In other words, you can see here, we have our primary, and the current will flow through this coil here and magnetize the core there, but no current, direct current, flows from these cables through over to these cables here. It's magnetically induced. So the magnetic field in here will be induced over here as well, and therefore you can have current flow on the output. But there is no current flow from this cable here all the way over to this cable here. They are isolated, completely separated from each other. Okay, well, why would we do that? There's a couple of reasons, but the main reason is to make the inside of our system floating. So on most systems, AC systems, let's say this is 120 volts AC, it's your house, the neutral will be connected to ground at your input connection into your house. Okay, so the utility company will connect the neutral directly to ground. Okay, but if you put a transformer in there, you can see that the secondary, if this was a one-to-one transformer, it's not a step down. We have just created a separately derived source. In other words, we have 120 volts between the two wires, but there is no connection to ground here. Okay, so we have given an isolation from that ground connection, which can be quite convenient for what we need to do. We'll go into this a little bit further. So if you measured from this point here, which is your hot for your 120 volts, down to a grounding terminal anywhere in your house or a ground pin in your socket, you will measure 120 volts. Okay, now, yes, if you go between your hot and your neutral on the output of a transformer, you will get 120 volts. That is correct. But remember, there's no connection to ground here. So if you went between hot and any ground connector on your house on the secondary of an isolation transformer, there's going to be no reference. So there should be no voltage. Now, yes, there can be some stray capacitance and other things in the cables that could give a ghost potential if you measured it with a very high impedance voltmeter. But there is actually no direct connection, and therefore, like if you connected a light bulb from hot to neutral on the input, yes, the light bulb would light, okay? But if you connected a light bulb from hot to ground on the secondary, the light bulb would not light. There is no current path. There is no connection to ground, so it would not light. And what that allows us to do is, if we added a rectifier, so AC in, DC out to the output of this system, therefore, when we connect a battery to the output of that rectifier, there is no reference to ground within our system. So therefore, if somebody goes to work on the battery, takes measurements, or wants to clean some terminals or something like that, it's very difficult for that worker to get an electrical shock when you have an isolation transformer, because there is no direct connection down to ground. Okay, now obviously, yes, if they went from the full positive to the full negative of the DC battery, they could subject themselves to an electric shock. But from any post of the battery down to ground, they would not get an electric shock. And also, a transformer blocks DC. So if you don't know about the design of a transformer, DC cannot pass through a transformer. You've got to build up and then collapse the field. And that's what AC does. And then that gets magnetically induced to the secondary. If you just put DC into the primary of the transformer, then it will saturate the transformer, and it blocks that DC from getting through to the other side, to the secondary of the transformer. So in truth, if you had a fault within your rectifier bridge and the DC was allowed to short circuit to the secondary, it cannot get from the secondary to the primary and impose DC onto your MCC, onto your 480 volts. It's impossible. It also reduces ground loops because of the isolation from ground, and it also attenuates noise. So they're all the reasons why we use an isolation transformer. Okay. So now we're going to talk about the battery charger rectifier. You can see it highlighted here in the single line drawing. And this is inside our 10 kVA UPS again. Now, this is going to be very simplistic, but this is actually how it works. So we have our three phases going in. So I'm going to call it A phase, B phase, and C phase. Okay. That's going in. So if you measured between this bus bar here and this bus bar here, if you had a 120 volt nominal battery, you're going to measure about 130 volts AC phase to phase. Okay. So once again, A, B, C, that is our input to the rectifier bridge. Okay. And then it's as simple as this. We have two bus bars here on the output of our rectifier bridge. One is negative and one is positive. And these black modules back here, they are our SCR packs. Okay. So it is quite simple. We have AC going into the bridge and we have DC coming out of the bridge. that is how our rectifier works. And it's this control board here. This is PCB1. There's a sticker there that says PCB1. This is our rectifier charger interface board. Okay, so that's the brains that tells the SCRs when to fire. And also you can see it's a little bit hidden here, but this is the gate drive board, which gives isolation between the printed circuit board here, which is a low voltage board, and obviously the gate drives to these SCRs on these terminals here, which is connected to 130 volts. So the gate drive board gives us isolation. So this board here does not see 130 volts. Okay. And also it gives a bit of oomph to the signal that we're sending to the SCRs to turn them on when we tell them to turn on. And then this aluminum back here, this is our heatsink. The SCRs are connected onto the heatsink. They're not electrically connected. It is just thermally connected. The base of the SCR is connected to the heatsink to dissipate heat in those SCRs. And then we have these fans on top that pull air through the heatsink to keep the SCRs cool. So that is in our single phase system, and it's even easier to see on our 30 kVA three-phase system. And remember, when I say single phase and three phase, I'm talking about the output of the UPS. Our rectifier bridges are all the same. We use three phase in. So once again, we've got 130 volts AC going in through to this terminal here. So we've got 130 volts. That goes into the black SCR, which is mounted here. And then once again, we have positive and negative coming out. This one here is our negative, and this one here is our positive. Okay, so AC going in and DC coming out. Simple as that. And then once again, you can see these connections to the SCRs. That is the gate drive signal to the SCRs. And obviously, once we get that, the reason that we do that is to store the DC in a battery. You know, that's why we have a rectifier in a charger inside our UPS system, so we can supply power to charge the battery at the correct voltage. Okay. And if you want to know more about actually how the industrial charger works inside an AMETEK SCI system, then you can go to our YouTube video library, and I created a video called Understanding DC Chargers and Rectifiers, and that explains in a lot more depth how the firing signals get sent to the SCRs, how the feedback circuit works. It's a lot more in depth. So if you want to find that, go to our YouTube site and type in the search bar, Understanding DC Chargers and Rectifiers. Now we're going to talk about the inverter, the part that's highlighted here. And obviously an inverter has DC on the input, and then it converts it to AC on the output. Okay. And in our single phase DPP system, our inverter bridge is behind this copper sheet here. That's a terrible circle. Let me draw it again. So this is our inverter bridge on our single phase 10 kVA DPP system. Okay, it's very difficult to see what's going on under there. You can see two terminals here. There is actually a DC capacitor behind there, a DC capacitor behind there, and then a DC capacitor behind there. And then these three terminals here, there's actually an IGBT module behind there. And an IGBT is a transistor. And that's what switches the DC to AC. So this is a laminated bus. this copper sheet that you're seeing here. So this, I'll draw it again here. So this copper sheet here is the laminated bus. And I know it's very, very difficult to tell, but when you've got a capacitor, you have one terminal that is positive and one terminal that is negative. Unfortunately, actually, I can tell because this says 12 and 12 is positive. So this outside copper that you can see is the positive DC going into the inverter bridge. And then this, you can see here there's a hole and there's white behind it. That white is transformer paper. It's insulating paper and it separates two sheets of copper. So right behind this sheet here is another sheet of identical copper that's separated by a transformer lamination. And so therefore they cannot touch each other. They don't short each other out. Okay. So that is the positive and negative that goes into the inverter bridge. And then there are two cables that come out. So there is this cable here. That is one of the outputs of the system. And then the other cable is not very clear in this picture. It's much easier in the next page I'm going to show you. But I think it's this one. No, that's the DC in. I think it comes out the bottom here and goes out there. Okay, so you have positive and negative going in, and then you have basically a hot and a neutral coming out. Much easier to see in the three-phase system. And this is the inverter control board, PCB3 and PCB3A. So this one here is PCB3, and the one that's mounted to it is PCB3A. We call that our UCB, or our universal communication board. Okay, and that's the where the firing signals that go to the IGBTs are generated. That is what turns the inverter on and tells it what to do. Okay. And here's the three-phase bridge that I mentioned earlier. And it's much easier to see the laminations and the three phases on this one here. So once again, we have a laminated bus. So this is our laminated bus, this portion here. Okay. And you can see we have our DC capacitors here. Okay. So this is our negative going in, and this top part is our positive. Okay, I just know that because this is 12, and from what I can remember, I think this is 13. So it would say minus 13, and it would say plus 12. Okay, and you can quite clearly see, so you see this bus bar going up here, and then it goes underneath this laminated paper. Okay, and then you can see that on top of the laminated paper is the positive. And I've got an inverter video that speaks about this, but the reason that we have a copper sheet on the negative separated by transformer paper and then positive on the top is basically whenever you have two plates separated by some insulation, you create a capacitor. So not only do we have all of these capacitors here, but we also have this capacitor that is created by our laminated bus. And that creates more capacitance and reduces the equivalent inductance of the inverter bridge, because inverter bridges don't like inductance. So the more capacitance, the more oomph we can give behind, and the less cable that we use, and we use copper bus, then the equivalent series inductance goes down. So that's our DC, and then our AC comes out on this bus bar here, this bus bar here, and this bus bar here. Okay, so you can see this cable that goes out. You can't see where the cable is connected because it actually goes underneath the inverter bridge and connects all the way up to there. And there's another cable that goes underneath the inverter bridge and connects up to there. But that is our DC in, and then our three-phase AC out. It is relatively simple, just like the charger. Instead of it being AC in, DC out, this is DC in and then AC out. Okay. And then this is for a three-phase system. This is the inverter board here. This is the inverter board, the PCB3 that we mentioned on the last page. But this actually lets you see the gate drive boards for each phase. So we also have gate drive boards. So this PCB3 creates the signals for the IGBTs, and then the gate drive boards takes that signal, basically amplifies it and gives it isolation, and then sends it over to the IGBTs. Actually, that's one thing I didn't show you on this last picture here. These are snubber capacitors, but behind these terminals here, you can see the white module here, and it actually goes all the way back here. So there's one IGBT module there, one IGBT module there, and one IGBT module there. And that's the same for each of the phases. So basically the way that our systems work is for 10 kVA, we'll use one IGBT, and for every 10 kVA above that, we will put another IGBT pack in parallel. Okay, so let's just say this is A phase, B phase, C phase. Then we can say that this is 10 kVA, 10 kVA, and 10 kVA. So we get 30 kVA out of this system. Okay. And once again, I said there's a more in-depth video. Here is what the video is called. If you go to the AMETEK SCI YouTube library, it's called Understanding How Inverters Work. And it tells you exactly how the transistors, the IGBTs, get fired, what they do, and how it works within our system. So hopefully, if you have time, you can go and check that video out at your leisure. The next component we're going to talk about is, on the single line diagram, the inverter output transformer. Okay. So this is on our 10 kVA single phase system. Once again, you can see I've circled here. It's very difficult to tell on your screen, but it does say TF2. So this transformer here was TF1. So now we have TF2, that is the inverter transformer. And the primary is at the back. You can see here, primary, and the arrows pointing to this terminal here and this terminal here. And the secondary is connected to this terminal here and this terminal here, okay? And I know it's difficult to tell, so I got a better view for you. So once again, our primary is this terminal here and this terminal behind the wire 16. You can see the copper bus bar that it's connected to here. And then our secondary is connected to this terminal here and this terminal here. And our secondary basically is the output of the inverter. It will be 120 volts AC, 60 hertz in North America, perfect sinusoidal waveform. Okay. And the input on the primary is a pulse width modulated signal, and I'll show you that on a screen in just a moment. And then for our three-phase system, once again, you can see TF2 here, and instead of just having a hot and a neutral, now we have three phases. So our primary is on the left-hand side, okay? And basically it's 1, 2, 3 tabs there. And then the secondary is basically this terminal here, and this terminal here. A phase, B phase, and C phase. And most of our 3-phase systems are 208, 120. Okay. So if you measured between this point here and this point here with a fluke, you would measure 208 volts. And once again, it's an isolation transformer, so it gives us isolation. So if there was a fault in the inverter bridge for some bizarre reason, and DC got onto the primary of the transformer, because of the isolation, that DC would not be allowed to propagate onto the secondary terminals, and you would not get DC going to your output circuits, which could damage pieces of equipment and cause a whole load of issues. So the isolation means the DC cannot propagate from the primary to the secondary. And this basically shows you what the input and the output is. So this red waveform here and the blue waveform here is our PWM going into the primary of the inverter transformer. So the primary is PWM, pulse width modulated signal. Now, this is just a very, so what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 26 pulses per cycle. Okay. That's just to give you an idea of what PWM looks like. Our system actually is 8 kilohertz. So we didn't want to put too much pulses on here because it would just confuse things. But just remember that is on the primary. This sine wave here, basically, that's a terrible line by me again, but the sine wave, the dotted line that you can see behind there, that is what you would see on the secondary of the transformer. With the help of the inductance of the transformer and the AC capacitors, we smooth out that PWM signal and turn it into a beautiful sine wave. Okay. That is why we use an inverter transformer. And then the last component that we're going to talk about in the single line diagram today is the static switch. Okay. Now, a static switch confuses a lot of people. I don't know particularly why, because really it's as simple as this is coming from the bypass. So this is your bypass static switch, and just think of it in your head as a switch. Okay. And it goes down onto this point here. And then this is the inverter output. And then we have a switch going to this point here. They're connected, both switches are connected together on the output. And basically, what we can do is we can switch the inverter switch on, and that allows power to flow from the inverter to the output. Or we can turn the bypass switch on, allowing bypass to go to the output. Now, the reason it's called a static switch is there's no moving parts. There is no mechanical switching, and I'll explain in a moment how we do that. Okay. So here is on the single phase system, we only switch the hot, we don't switch the neutral. So you can see here, we have our inverter terminal here going to this bus bar here. Then we have our bypass going onto this bus bar here. Now, once again, we have an SCR pack behind here, and we have an SCR pack behind here. So if we go back to the previous slide, this is our inverter SCR pack, which is this pack here. And this is our bypass SCR pack, which is this pack here. And as I said, both switches on the output are connected together. So this bus bar here is the output of the static switch, and that goes out through a CT out to the load circuits connected to the UPS. So basically, once again, think about it just like a switch. So we have a switch here, and we have a switch here. And through either the push buttons on the front of the UPS or automatically through our sensing circuits, we can choose either the inverter to load or the bypass to load. Now, what the UPS does as per its design, it does everything it can to try and keep the inverter on load at all times, because that's connected to the DC bus and the battery and creates a beautiful sine wave and isolates you from any sags or any power fluctuations on your bypass. So we always want to keep it on inverter as much as we possibly can. And it's only if something happened to the inverter and the inverter stopped working that we would say, okay, we need to switch this bypass switch on and allow bypass to flow through here and out through that cable there. Okay. But it is relatively as simple as that. We either tell the inverter static switch to be on or the bypass static switch to be on. And then whenever we transfer between the two, it's a seamless transfer. And I'll just explain why. Because if you have a sine wave, SCRs do not switch off by removing a gate signal. SCRs will only switch off at the zero crossing point of a sine wave. So basically, if you are on inverter at this point here, and then at this point here, you want to transfer to bypass. So from this point here, we're going to bypass. What happens is both the inverter static switch and the bypass static switch will be on at the same time until we get to this zero crossing point. And then after that, we will be on bypass only. So it is always going to be a make before break transfer. So it's nearly impossible, unless there's an issue with the SCRs themselves, to have a transfer between inverter and bypass that causes a blip on the load. That's the design of the static switch. And for a three-phase system, a little bit more complicated, but you can see once again, we have our inverter A phase, B phase, and C phase going in, and then we have a static switch. So basically we have an A phase static switch, a B phase static switch, and a C phase static switch. And they all get the same gate drive signal sent to them at the same time. But basically we can choose, if we had the inverter to load push button pressed, then we would be connected there, there, and there. So therefore the inverter would flow out through here, out that cable to the load. It would flow through this cable out to the load and through this cable out to the load. Okay. And if you press the bypass to load push button, then bypass would come in here. You would switch that on and it would go out through the same cable out to your load circuits. It really is as simple as that. And then on a single phase system, PCB 11 is our our static switch gate drive board. There's actually two LEDs that it tells you if an SCR has failed, and inverter to load LED there as well. Okay, but that's the interface between the inverter static switch control board and the the static switches themselves. Remember, there's always isolation between the control board and the SCRs. So this is our inverter gate drive board. And there's the same for the three-phase system. Okay, you can tell there's 1, 2, 3 transformers there, isolation pulse transformers going to the SCRs. Okay, so that is the end of what goes inside our UPS systems. And hopefully that gives you more of an understanding when you open the door, what the components are and where you can find them. So let's have a look and see what questions we have been asked. And this is an ideal situation. If you have any questions regarding this presentation or any other questions, you can type them in the Q&A chat bar now. So first of all, what would the effect of too much inductance be on the inverter bridge? That's a very good question, Elizabeth. Too much inductance on the inverter bridge, especially when you're switching transistors at a high frequency, what you're doing is you're opening and closing a connection. And whenever you have inductance flowing through, current flowing through an open and closed switch, and there is a higher inductance, it causes a back EMF. Basically, you're interrupting the current through an inductor. The inductor builds up a field and it's trying to push that, keep the current the same. An inductor basically tries to keep the current the same flowing through it at all times through its magnetic field. So basically you will build up a high back EMF across the collector and emitter of the IGBT, and it could cause the IGBTs to fail. So that's why we try and keep the inductance as low as possible, so we don't put an overvoltage back EMF strain caused by the inductance, and try not to blow up the IGBTs, basically. So hopefully that explains why we try and keep the inductance low, Elizabeth. Another question, what impact to the charger inverter would a DC arc fault at the batteries be? Good question, Isaac. In truth, it's difficult to tell. Probably nothing, because you've got, the battery is usually separated by a length of cable. That cable has resistance and it has some capacitance in it. So if there was any kind of little spike caused by the arc fault, I can't see it causing an issue into the charger inverter bridge. If the arc fault was due to a short, then the charger is going to see that short as well because it's connected in parallel, but it will current limit itself and should protect itself from being damaged. And you may see the DC bus drop if it is a direct short as well. So the inverter may see that, but it would just transfer to bypass. So they're worst case scenarios if you have an arc fault on the battery, but I'd need to know more about what kind of arc fault. If it was a short circuit, what was going on. If you just dropped a wrench across the battery, basically the battery would just evaporate the connection between the positive and negative very quickly, because the battery has so much current ready to give, and I can't see it affecting the UPS too much, to be honest, if the UPS is designed correctly. Let's see if anybody else has any questions. I only see 2 questions just now. So we inspected a transformer near the AC capacitors that shows both white powdery substance and has evidence of discoloration and overheating. Is this a concern? So that's from Ali. I'm guessing that's not on a DPP system. That'll be on our older microfarad systems. We call them the SE range of systems. And they have a ferroresonant transformer in it. It's not a PWM system. And if you see that there is white powder, discoloration and overheating, then is it a concern? I would say it's something you need to start worrying about and looking to maybe replace that transformer. The white powder is caused by the vibrations in the lamination of the ferroresonant transformer. And basically it's the varnish that covers all of the steel laminations within the core of that transformer. It's that varnish basically breaking down because the laminations are vibrating. So what you always tend to find when you see that white powdery substance and the transformer is heating up, then the noise from that transformer will tend to also go up because the vibration is getting worse. And it is basically a snowball effect. Eventually it will just get worse and worse and worse. And most times when it fails, the installation breaks down completely, and it allows one of the power, whether it's this primary or the secondary, it will allow a path to ground eventually, and the system will transfer to bypass. So I would say yes, contact AMETEK, and we can start looking into that for you. Here's a question, another question. Hopefully that explains what you're seeing there, Ali. Ernest is asking, is the UPS derated for altitudes above 5,000 feet? That's a very good question. I can't remember if I have. I don't think I do have a spec sheet with me. Actually, I do for one of our older systems. I don't know if it has anything about altitude. In truth, that would be one of our design engineers who would answer that question for you. I do not see anything. Oh, operating altitude. There we go, 10,000 feet. So we can go up to 10,000 feet without derating anything. So I'm glad I looked at that. So Ernest, yes, above 5,000 feet, we are good. Above 10,000 feet, I'm guessing we do have to start derating. Let's see if there are any more questions in the Q&A section. Oh, Ben, for 3,300 without derating. Well, it was the DSE manual that I looked at, and it does say 10,000 feet. So we should be good. Any other questions? So while I wait to see if there's any more questions, I would like to say thank you very much, everybody, once again, for attending. I know that everybody is extremely busy, and for you to take time out of your day to listen to me waffle on about UPSs, I think that's fantastic. I really do appreciate you taking the time to do that. I hope you got something out of this presentation. I hope you know more about our UPSs when you open the door. As always, you're going to receive a survey after this webinar is finished. I really would appreciate if you fill it out, because I think it's question 5 that asks what you would like to see me talk about in our next webinar. And I'm really interested to find out what you want me to talk about, what things that you see out in the field that you would like to be discussed, anything about the design of the system that you still don't understand. Fill out that question. I read every single one of them, and I do tailor my webinars based on those responses. London has put the details in the chat bar. If you want to contact us, you can use the web link and contact us via the web link. You can email sci.marketing@ametek.com, or you can pick up the phone and call 1-800-635-7300. You just have to go through one menu tree, and then you'll usually get to a human being, and we'll try and help you out. And once again, she's put the link to our YouTube channel, and within 24 hours, this video will be available to you for you to rewatch, share to the world, and do whatever you want. So it doesn't look like I have any more questions. So I'm just going to say once again, thank you very much for joining us for this AMETEK Solid State Controls webinar, and hopefully we'll see you again next month. Take care, everyone.